introduce Pedram, who's just through the wall from me. He's going to talk on holomorphic bundles on foliations.
All right, thank you so much, Rod, and thank you everyone for showing up. So yeah, this is let me see if this works. All right. So this talk is about I guess it's going to lean a little bit more on the geometry side, but there will be some analysis in the proof. So I hope to at least get some ideas in the proof. So hopefully it does the session justice. So the talk is about the general correspondence, and the outline is that I will try to give a bit of background and motivation, especially from gauge theory, which is sort of what sort of caused my interest in the subject. And then sort of outline what the appropriate definitions are in the foliated setting, and then finally discuss the how the correspondence extends to foliations and some interesting applications that follows from this theorem. So this is all a joint work with David Braglia at the University of Adelaide in Australia. Right, so before getting started, let me actually state the theorem that we want to extend to the foliated setting. We're looking at holomorphic bundles on compact Hermitian manifolds. And the correspondences give you, if and only, well, necessary and sufficient condition for the existence of Hermitian-Einstein metrics on holomorphic bundles. So a Hermitian metric is Hermitian-Einstein if it satisfies the following equation, namely the mean curvature of the Chern connection associated to the metric is a constant multiple of the identity endomorphism. And the Hitchin-Kobayashi correspondence characterizes the existence of such solutions, namely such solutions exist exactly when the bundle is polystable. So I will get to the definition of stability for those who haven't encountered it before. This is a part of a very long story. So before giving sort of the motivation of gauge theory, let me just give a quick overview of what the background to this theorem is. So the first instance of this was studied in the case of Riemann surfaces, and in that case, the Hermitian-Einstein condition is exactly the condition that the curvature is the connection is projectively flat. And this is a result by Narasimhan-Seshadri. So the projective flatness, you can, by the non-general representation, you can think of it as a representation of the fundamental group. So the statement was given as a relation between the moduli space, so the character variety of the fundamental group into unitary group, and on the other side is the moduli space of polystable holomorphic bundles on the Riemann surface. In the early 80s, Kobayashi extended from Kähler-Einstein metrics on the tangent bundle. He introduced the notion of Hermitian-Einstein connections on holomorphic bundles over Kähler manifolds, and he was able to prove the sort of a simpler direction, namely that the existence of a Hermitian-Einstein metric implies polystability. And just a year later, Donaldson gave the sort of the more difficult directions, showed that polystability implies existence of Hermitian-Einstein connections. And the technique he used was the heat equation. This was successively generalized to algebraic surfaces and then to arbitrary surfaces. And then by Uhlenbeck and Yao, it was generalized to Kähler manifolds. And the technique here is the continuity method, which is the method we can apply in the foliated setting. All right, so before getting into the setup in the foliated setting, let me give you a bit of motivation why you would be interested in this question for foliations. So one motivation for studying these Hermitian-Einstein metrics comes from gauge theory, namely on a compact Riemannian form manifold, you can study particular solutions of the Yang-Mills equation called Instanton equations. And if you have a Hermitian structure on your form manifold, decomposing the forms into self-2 and self-2 parts, the instanton equation becomes this set of equations here. So the first equation is an integrability condition. So it tells you that the unitary bundle carries a holomorphic structure. And the second equation you see is exactly the Hermitian-Einstein equation for a trivial Einstein factor. So the study of instantons on Hermitian form manifolds is the equivalent to studying the Hermitian-Einstein connections. And in fact, the statement, even though it's a statement about the individual bundle, is really a statement about between moduli spaces. So the moduli space of rank R instantons on Hermitian form manifolds is the same as the Hermitian-Einstein equation with Einstein factor, trivial Einstein factor, which corresponds to trivial degree for the vector bundle. But the Hitchin-Kobayashi correspondence, that's the same as studying polystable holomorphic bundles. So this gives you an avenue to study instantons through complex analytic techniques. And so foliations, you stumble upon it if you start looking into a generalization of instantons to high dimensions. So this kind of equation was studied in the 80s again by physicists, and it was brought to so popularized in the mathematics literature by Donaldson and Thomas in the late 90s. So namely, if you have a distinguished form on your manifold, omega, then you can generalize with of appropriate degree, then you can generalize the instanton equation as such. So in particular on a Hermitian N manifold, a suitable omega would be an appropriate power of the Hermitian form. And of course, on special holonomy manifolds like G2 manifolds, spin 7 manifolds, there exists distinguished calibration forms they can use for as a choice for omega. And again, these equations are equivalent to Hermitian-Einstein equations for its trivial Einstein factor. Another setup where you can encounter this kind of equations is if you're on a contact 5 manifold. So in that case, you can pick omega to be the contact 1 form, and you get these equations. This is qualitatively different from the instanton equation up here because omega is closed in these examples that I mentioned, but of course the contact form is not a closed form. But nevertheless, the anti-self-dual contact instanton equations satisfy the Young-Mills equation. And what happens here is that since on the contact form you have the one-dimensional rep foliation, and on a Sasakian manifold, so transverse scalar, these equations are equivalent to looking at connections that are basic with respect to this rep foliation, and they satisfy the usual Young-Mills transfers to the foliation. So this is one motivation of looking at this Hitchin-Kobayashi in the foliate setting. Let me just mention that these contact instantons equations that we've looked at previously, they come from a certain dimensional reduction of a 6-dimensional superconformal field theory. So it's supposed to live by dimensional reduction on dimension 5. And this theory sort of underlies a lot of the recent progress in various branches of mathematics. So it's a very nice diagram. I'm not going to go into more details on this subject, but I just want to mention that it fits into this picture. So the partition functions in physics localize onto the moduli space of these contact instantons. And so 5 is actually another very distinguished dimension. You can define these contact instanton equations in any on any contact 2n+1 dimensional manifold. And in particular for Sasakian, again, there's omega contact instanton equations where omega is now an appropriate power of the contact Liouville form, if you like. These are again have an interpretation as being basic connection to the with respect to the rep foliation, and the contact instanton equation become exactly the Hermitian-Einstein equations on Sasakian manifolds. So this on a Sasakian manifold, of course, the rep foliation is a taut Riemannian foliation. So with the transverse scalar structure, so this kind of naturally raises the question whether this Hitchin-Kobayashi correspondence extends not just to Sasakian manifold, but more generally to any compact foliated manifold with a transverse Hermitian structure, so more general than Kähler. So I guess the bottom line here is that the answer to this question is yes, you need some condition on the foliation, namely that it's taut. So in particular, Sasakians satisfy that condition. Other examples, of course, 3 Sasakians or co-Kähler structures. So there's a lot of interesting examples where that satisfy the requirements for extending this Hitchin-Kobayashi to the foliated setting. All right, so in the remaining time that I've left, I'd like to say a few words about how to extend the 2 sides of the correspondence, namely the Hermitian-Einstein metrics and the notion of stability, to the foliated setting. I'll say a few words about how the continuity method proof of Uhlenbeck and Yau extends to the foliated setting, and then I finish with some applications. So there'll be a couple of definitions here, but hopefully most of them are familiar if you're familiar with foliations. So the setup is we're on a oriented M manifold with a codimension 2n Riemannian foliation. So Riemannian foliation means that you have a bundle-like metric such that locally the foliation is a Riemannian submersion. And we denote by psi the leaf-wise volume form, and H is the normal bundle for foliation. And tautness is a condition that the manifold, the foliation admits a metric such that each leaf is a minimal submanifold, meaning the mean curvature form on the leaves vanishes. And we like to effectively, doing Hitchin-Kobayashi and foliation, means that we want to really work on establish such a result in the leaf space. So the differential forms on the leaf space are exactly the basic differential forms on X. So there are sections of the horizontal distribution and invariant in this sense. And why we need to restrict to tautness is because to establish a correspondence, we need to define the notion of stability, and the stability is defined in terms of the slope or the degree of the bundle. And to make have a sensible notion of degree in the foliated setting, we will need to use a basic version of Stokes' theorem, which is what's stated here. So without this, there is no immediate sort of natural way of defining the degree for transverse holomorphic bundles. So maybe standard results, I won't say too much about the basic Stokes theorem. And again, we were working in the complex settings. We need that our foliation is in fact equipped with a transverse Hermitian structure. So again, the definitions are generalized straightforwardly. We have an integrable complex structure on the horizontal distribution with associated Hermitian 2 form. And this gives rise to a Lefschetz operator and its adjunct, the contraction operator, on the space of basic differential forms. And moreover, the complex transverse complex structure gives you the standard splitting into PQ forms. Also, the notions of holomorphic bundles extend to the foliated setting in a standard way. We say that a bundle is foliated if its frame bundle is foliated, and a foliated principal bundle, maybe the most economical way of defining it is in terms of a clutching construction, and it's foliated if it's you can choose these transition functions to be basic function with respect to the foliation. A connection on a foliated principal bundle is basic if the connection form is basic form. And we say that a foliated vector bundle has a transverse Hermitian metric if it's the metric form. Once you compose it with sections, it's a basic function on the manifold. And an important remark here is that there's actually an obstruction to the existence of basic connections on principal bundles. There's a secondary invariant that obstructs it. And similarly, not every foliated Hermitian vector bundle admits, a foliated vector bundle admits the Hermitian metric. And this is essentially both facts are due to the fact that given a covering, you cannot necessarily find a partition of unity subordinate to that cover consisting of basic functions. So in general, to define the notion of degree, we will have to restrict to holomorphic bundles that admit transverse Hermitian metrics. And the notion of transverse holomorphic structure again extends naturally to the holomorphic setting. The Chern correspondence relates transverse holomorphic structures to unitary connection of type 1-1. It also has an extension to the holomorphic setting. And as I mentioned, we want to work in a more general setting where our manifold is not only transverse scalar, but transverse Hermitian. So now in order to define a degree for our bundles, we have to restrict to metrics that are Gauduchon, meaning the associated Hermitian form, transverse Hermitian form is DD bar closed. But again, using sort of standard maximum principle, you can prove that every conformal class of these transverse Hermitian metrics admit a Gauduchon metric, meaning you can scale it by a basic positive real values function. And in fact, this function in dimensions 2 and higher is unique if manifold is connected. Sorry. All right, so this is all the background we need. So we can define one side of the Hitchin-Kobayashi correspondence, namely a metric on a foliated Hermitian bundle over a foliated Gauduchon manifold is it admits is a transverse Hermitian-Einstein if its Chern curvature is if the Chern connection rather has curvature that's type 1-1 as satisfied this. Actually, the way I wrote it now is I don't assume there's a holomorphic bundle, but yeah, so being type 1-1 means that you equip the bundle with a holomorphic structure and it satisfies the usual Hermitian-Einstein condition, but everything is with foliated now, so these are basic connections. And we say that the metric is transverse Hermitian-Einstein if it's associated Chern connection, satisfied the Hermitian-Einstein equation. All right, so this takes care of one side of the Hitchin-Kobayashi correspondence. The other side is the notion of stability for our holomorphic bundles, transverse holomorphic bundles. So, so this is where we will need the manifold is Gauduchon. So given a foliated holomorphic bundle with a transverse Hermitian metric, the degree is defined as usual, the Chern class of the determinant bundle of E. So we use this Chern-Weyl definition, and so we have a metric H on our foliated bundle, and this is a priori it would depend on the choice of metrics, this definition, but it turns out that if you change your metric, this trace of the Chern connection curvature of the Chern connection will change by exactly a DD closed form. So now you can use the fact that your manifold is Gauduchon and use the basic Stokes theorem to show that this definition is actually independent of the choice of transverse Hermitian metric on E. So this takes care of the notion of a degree, and if you divide the degree by the rank, you get the slope for your holomorphic bundle, transverse holomorphic bundle. In order to define the stability, we need to consider a bit more general setting. Not only holomorphic subbundles, we need to look at transverse coherent subsheaves of a holomorphic bundle. So again, this coherent sheaves are defined in the usual way. We restrict to basic holomorphic functions on X. So if this is O denotes a sheaf of such functions, then transverse coherent sheaf is just a sheaf of all modules such that the local is the co-kernel of appropriate powers of this structure sheaf. For the definition of stability, we just need the transverse coherent sheaves which have a torsion-free quotient. So this property that such sheaves are essentially holomorphic bundles outside of a subvariety of codimension at least 2, this still holds. Of course, everything is not transverse, so you have this holds in the transverse direction, and we have no condition in the leaf direction, but we're working basically. So yeah, maybe don't go into this exact definition of what it means to be in transverse analytic subvariety. it means that locally it's a zero locus of finitely many basic holomorphic functions. So let's leave it at that. And now as to, we immediately face an issue here is that to define a degree for these transverse coherent sheaves, we want to define the determinant. That still is done in the usual way. Pick a finite local resolution, and you can define the determinant as the product of alternating determinants, that it gives you a line bundle, a basic line bundle. But the problem you face here is that even though your original bundle EA has a Hermitian metric, it does not imply that the determinant line of this transverse coherent sheaves will inherit the metric. So to get around this issue, we use a foliated version of Hironaka's resolution of singularities. So first of all, let GRSE denote the Grassmannian bundle over X for S is a fixed positive integer less than R. So now a subbundle of E is simply a section of this bundle, right? So there's a tautological bundle of this Grassmannian, and if you pick a section of Q and pull back this tautological bundle, that gives you a subbundle of E. So to work with these more general coherent subsheaves of E with torsion-free quotients, we want to generalize, we need to consider meromorphic function sections of Q, or another way of saying that is that you look at closure of such, well, because these sheaves are subbundled outside of a codimension 2 analytic subvariety. Outside you get a section of a holomorphic bundle outside of the singular set, and then by taking the closure, that gives you a closely reducible subvariety of the Grassmannian, and this in fact gives you a correspondence between these sheaves. So another way of thinking about these sheaves is in terms as closely reducible transverse subvarieties of the total space that map generically isomorphically onto the base. So the purpose of this slide is to tell you that there is another way of characterizing these sheaves, and the problem we're trying to circumvent here is to define the notion of a degree for these subsheaves, which you cannot do automatically because you don't have a transverse metric on the determinant lines. And now this Y is of course singular in general, but you can prove this foliated version of Hironaka's resolution of singularities. Again, the details of the proof, I'll omit that, but the basic idea behind this theorem is to do desingularization, pick a local foliated chart, do desingularization locally, and then argue that you can glue these local desingularizations globally to get a foliated manifold Y tilde. And this essentially relies on a functoriality of these desingularizations. So that's the idea behind the proof. But the bottom line is you get a foliated resolved manifold that maps isomorphically onto the smooth locus of the subvariety Y. And this is pretty much what we need to define the degree for our transverse coherent subsheaves. So again, given such a subsheaf of rank S, that's the same thing as picking an irreducible closed analytic subvariety of the total space, the Grassmannian. And now we pick a transverse resolution, Y tilde. So this gives us this picture here. So you have a bundle, you have a coherent subsheaf with torsion-free quotient, curly F. And we have the tautological bundle over the Grassmannian bundle, and what we do is that such a subsheaf F is the same as an analytic subvariety Y. You pick a resolution Y tilde, you pull back the tautological bundle to Y tilde, and now the tautological bundle naturally embeds inside the pullback of the holomorphic bundle E. So the metric, Hermitian metric, transverse Hermitian metric on E restricts to the tautological bundle and pulls back to Hermitian metric on the pullback bundle of the Y tilde, of the resolved manifold. So what I just said is summarized in this sentence. You get a transverse foliated bundle. You get a foliated bundle over the resolution with a transverse Hermitian metric inherited from E. So now you take the associated Chern connection, denote that F1 tilde, and now you can define the degree of these torsion-free coherent subsheaves in the usual way, using the Chern formula. And you can show that the pullback, the preimage of the singular locus of Y has measure 0. So this is in fact independent of the choice of transverse resolution. All right, so any questions at this point? There's a nope. All right, so this of course, now we have all the ingredients that we need to define notion of stability. This is done in the US in the foliage setting as it's done in the usual way. The transverse holomorphic bundle is that admits a transverse Hermitian metric is stable if for all transverse coherent subsheaves of rank less than the rank of the bundle, and these sheaves would have torsion-free quotients. The slope of the sheaf is bounded by the slope of the bundle E, and it's polystable if it decomposes into direct sum of stable transverse holomorphic bundles of the same slope. And if you don't, if the bundle doesn't have any non-trivial basic holomorphic endomorphisms, meaning all of them are multiples of the identity endomorphism, then the bundle is called simple. So particularly being stable implies, transverse stable implies that it's simple. And then the result is, and the statement is pretty much the same statement as you have in the non-foliated setting, but there are a few subtleties that we sort of surmounted. So the transverse Hitchin-Kobayashi correspondence gives you a necessary and sufficient condition for the existence of transverse Hermitian-Einstein metrics, namely that the bundle is polystable. And if your bundle is simple, then the metric is actually unique up to rescaling. All right, so that's the statement of the theorem. The proof proceeds in the same way as the Uhlenbeck-Yau proof. There are a few subtleties that needs to be addressed, namely, is it work in the foliated setting, we have to deal with the transverse elliptic operators and use basic subleft theory. So there are a few things that needs to be modified, but the basic idea is the same as the Uhlenbeck-Yau proof. So let me say maybe a couple of words about the proof. So the simpler direction is to show that existence of Hermitian-Einstein metrics implies polystability. So again, given a coherent subsheaf with torsion-free quotient, we know that it's outside of a codimension transverse codimension 2 subriety. It's a holomorphic bundle. So let F denote this corresponding subbundle. Then you can show that the relation between the trace of the curvature F1 on F and the trace of the Chern connection of E is exactly, they differ exactly by the norm of this differential of the projection. So pi is the projection from E onto F. So now integrating this expression over X and using the Hermitian-Einstein equation on the term, the first term on the right-hand side, you can rewrite this as a multiple degree on the left equals the slope, well, the expression on the right-hand side. So in particular, if you divide by the rank of the coherent subsheaf, it tells you that the slope of the sheaf is less than equal to the slope of E, and equality occurs exactly when the differential of the projection is 0. And using this projection self-adjoint, it also tells you that the del bar of pi is 0. And so in particular, it's a covariantly constant. Now using the Hartog's theorem, you can extend this projection onto the sheaf subbundle to the entire space X, and using the fact that the projection is covariantly constant, it means that the orthogonal complement of the subbundle F is also stable of the same slope. So this gives you splitting of the bundle into direct sum of either stable bundles or polystable. But if it's polystable, you keep repeating this argument. All right, so that's one direction, and the other direction is using the method of continuity. So the idea is to rewrite the Hermitian-Einstein equations in a way that we can sort of introduce a perturbation and then use the strategy of the continuity method. So given a fixed transverse Hermitian metric in your bundle, any other metric, transverse metrics, can be written as such. Namely, it's a original metric, the fixed metric, composed with positive definite Hermitian endomorphism. That's basic, of course. Everything is basic in this setting. And now it's easy to check that the Chern connection of the metric H is related to the Chern connection of H naught as such. So if you introduce this operator L naught, then the Hermitian-Einstein equation for the metric H is precisely the map F, this endomorphism F, lies in the kernel of this operator L naught. So this is our equation, and we want to show that if your bundle is polystable, there exists a solution to this equation. So the way to proceed is to introduce the perturbation of our operator, and then they introduce this epsilon times this log of this bundle map, and then again we proceed by first constructing a solution for so epsilon here is a real number in the interval 0 to 1. We construct a solution for epsilon equals 1. This is quite straightforward to do. Just by rescaling the metric, you get a solution. And then we want to look at the subset J of all real numbers epsilon for which there exists a solution to the equation, L epsilon prime, F epsilon prime. So in particular, we know that J contains 1, and then again, using some a priori estimates, you can prove that this interval has to be open and closed. Those obviously details I'm omitting here. And then the final idea here is to take the limit as epsilon tends to 0, and you show that either if there exists a solution, then it has to be a transverse Hermitian-Einstein metric, and if the solution does not exist, then you can construct a transverse coherent subsheet that violates the stability condition. So that's in broad strokes, that's the idea behind the proof. And in the few minutes that's left, let me give you a couple of applications of our transverse Hermitian-Einstein, Hitchin-Kobayashi correspondence. So the first situation one could look at is the case of an analog of a Riemann surface, namely if you look at a compact Hermitian foliation codimension 1. So there's a couple of simplifications that happen in this setting, namely it's actually sufficient in this case to only consider holomorphic subbundles of E, since by dimensional reason. And transverse Hitchin-Kobayashi correspondence takes a simpler form, namely that a holomorphic bundle admits a Hermitian-Einstein is a typo here, Hermitian-Einstein metric if the curvature is projectively flat. So this is a transverse version of the Narasimhan-Seshadri theorem. So if your manifold is foliated by so what would be a codimension 1 foliation. And in particular, if your bundle has degree 0, so that the connection is flat, then you get this very sort of nice interpretation of the character varieties for for your manifold, and of course, the manifold X is in any dimension. So you can, the Hitchin-Kobayashi correspondence tells you that this character variety is the moduli space of polystable rank R degree 0 transverse holomorphic bundles admitting transverse Hermitian metrics. An important point here is that obviously on the left-hand side, we don't see the foliation, right? So it's just a representation of the fundamental group of the total space. What it means on the right-hand side is that you have a moduli space of foliated bundles, but you have to allow for all possible transverse structures on your holomorphic bundle. So if you fix the transverse structure on the right-hand side, then you would just get a subset of representation of the fundamental group. And in fact, we don't expect those subset or subvarieties of the character variety to be closed. In fact, you can easily construct examples where if you fix the transfer structure in your holomorphic bundle, then the corresponding moduli space is not compact. So in particular, the Uhlenbeck weak Uhlenbeck compactification theorem fails for a fixed transfer structure. So you cannot find a sequence of basic connections uniformly bounded for in any Sobolev norm, such that you can find a convergent subsequence. All right, so my apologies, there's a construction happening here. I'm not sure if you can hear me well. All right, so let me mention maybe two other applications of the Hitchin-Kobayashi correspondence, namely consider a setting where you have a compact Hermitian manifold, Godeshan manifold, and acted upon by a finitely presented group. So let me just remind you, there's a very a neat way of showing that such fundamental groups, such finitely presented groups can be realized fundamental group of a closed-oriented form manifold. And the idea is due, I believe, due to Kerver, is you take connected sum of S1 times S3, and each circle factor corresponds to the generator in your fundamental group, and every relation corresponds to a loop inside your manifold Z. So the idea to construct this manifold Y is to do surgery along these loops. So you cut out the tubular neighborhood of these loops correspond to each relation in your group G, and then you the tubular neighborhood is homeomorphic to S1 cross 3 ball, and the boundary of the 3 ball is S1 cross S2, which is also the same as the boundary of the 2 ball cross S2. So you cut out this tubular neighborhood and you glue back in a copy of D2 cross S2. And you can use this type of van Kempen theorem to show that this surgery is exactly killing off that relation. All right, so that's a well-known result that finitely presented groups can be thought of as fundamental groups of closed-oriented smooth form manifolds. So we can use this in the following way. We consider the universal cover of this form manifold Y, and then construct the quotient M cross the universal cover quotient by G. Then it's easy to check that this is a compact-oriented taut transverse Hermitian foliation. In fact, transverse Godeshan, since we picked M to have a Godeshan metric. And the notion of transverse holomorphic bundle on the X is the same as G equivariant holomorphic bundles on M. So now applying the transverse Hitchin-Kobayashi correspondence to our X here, this gives you the following equivariant version of Hitchin-Kobayashi correspondence for finitely presented groups, namely G equivariant holomorphic bundle admitting G invariant Hermitian metrics, admit a G invariant Hermitian-Einstein metric if and only if it's polystable. I'm quickly running out of time, so let me just quickly mention that there's another application of the equivariant Hitchin-Kobayashi correspondence is that it implies an orbifold refinement of the Narasimhan-Seshadri theorem. So let me maybe, because I'm almost out of time, let me skip this. And just to return to the question of higher dimensional instantons, remember I said that you can define, it's a very natural notion of there exists a natural notion of contact instantons on any contact manifold, in particular on Sasakian manifolds. The high dimensional instantons are exactly the transverse Hermitian-Einstein connections. This transverse Hitchin-Kobayashi correspondence applied to Sasakian manifolds tells you that this high dimensional instanton moduli spaces, the anti-subdual ones, corresponds exactly to the moduli space of polystable transfer holomorphic bundles. And an instance of this result was actually shown earlier by Bistros and Schumacher under the condition that the Sasakian foliation is quasi-regular. All right, I think I'm out of time, so I'll stop here.